right, but I wanted to go ahead and start off with a question today. This one is not like the riddle, okay? So this one is a little bit less tricky in that regard, okay? But our question here, and this is going to be really helping us sum up everything that we learned about electron transport chain, but it says this: it's an individual is found dead next to a bottle of Tylenol in a pool of vomit. Autopsy report demonstrate that the individual had a massive damage to their lungs and heart, leading to their death. Furthermore, lactate levels in the blood were up, as were NADH levels, while NAD plus levels were low. Blood oxygen levels were fine, however. Blood oxygen levels were fine. However, all signs point to the fact that this individual died of hypoxia. Okay, how can this be explained? So, you got 2 minutes. Talk to your neighbor about this. What do you think is causing these results? Try and take into account. I mean, you don't have to explain why NADH levels are high and NADH levels are, or NAD plus levels are low, and lactate levels are high, but that's certainly some clues there, okay? All right, so talk to your neighbor about this. I'll give you a minute. I actually can give you 2 minutes on this one, okay? Go. About 30 seconds left, so go ahead and submit that answer.
Can I give a little more time? I'm trying to write, but I have a long answer.
Okay. No, go ahead and submit something, and then I know, I'm sorry. Okay, 10 seconds. Stressful. Okay. All right, if you didn't get an answer in, come and see me, okay? After class, I'll give you credit for being here. Okay, so let's go ahead and look at these results here. Okay, so alveoli are broken. No, the donating of electrons from NADH to FMN was inhibited, leading to forever sleep. Okay. They died from electron transport chain. Okay, NADH production was slow due to extreme concentration of acetaminophen in the liver. Okay, hypoxia reduces the flux of aerobic respiration. RS production lack antioxidants. Okay, so electron transport chain is not working. Okay, magic. Someone said magic. Okay, something is not. Okay, so there's the Rockies didn't lose. Okay, yeah, okay. The Rockies didn't lose today. It is a good day to be a Rockies fan, and the reason is because they can't lose today. It's a good day. The previous 8 days haven't been so great though. But anyway, again, if they score more runs than the other team, then we should have no problem. But that's not happening. All right, so there's some interesting answers as I kind of glance through these. I'm going to go ahead and highlight this one. Something is not allowing oxygen into the inside. That's the kind of of what we're looking at here. And then we've got something here. This is kind of hinting around the right answer as well. The donating of electrons from NADH to FMN was inhibited, leading to forever sleep. Okay, something along those lines. So there could be a number of different explanations for this as we look at these pieces of data. Well, let me give you one plausible answer, okay? The reason I highlighted some of them is because they were indicating that maybe the electron transport chain was inhibited in some way, okay? And that is indeed a good explanation of the data. So we come back here, okay, and those results are probably most consistent with something called cyanide poisoning, okay? So cyanide is a notorious, of course, toxin, and the Tylenol is more of a red herring. Actually, interestingly, I think it was in the 1970s, there was, I think in the suburbs of Chicago, someone slipped into a drugstore and opened up multiple bottles of Tylenol and dumped cyanide in them, so laced the Tylenol with cyanide. Ended up killing about 10 to 15 people. All of them had symptoms like what was just described here. That, of course, led to, you know, the impossible packaging that we find today. Don't use this if the seal has been broken. That kind of thing that didn't that those weren't present in the 1970s. Okay, but interesting. Let's just look at one explanation of this data, and let's just say that it was indeed cyanide poisoning. So cyanide is a really simple molecule. It's just C triple bond to a carbon triple bonded to a nitrogen with a negative charge on it. All right, but cyanide will block this process. Okay, so we'll just put a little C in there, and we'll just say that then oxygen can't be used. Right, now that would explain then hypoxic type symptoms despite levels of oxygen being normal. Okay, blood plasma oxygen levels were normal, but oxygen wasn't being utilized by tissues because cyanide had sneaked into the mitochondria, bound to, actually it binds to heme A3 on complex 4. Okay, I showed you at heme A3 on complex 4, there's an oxygen binding site on that heme group. Cyanide can form a covalent bond to that. It's actually stronger than oxygen bond to that. Okay, and so it's a competitive inhibitor of that. Now, what that does then is that electrons can still enter into the electron transport chain through the various sources that we've talked about, NADH, and of course succinate, and other sources. However, there's no way for those electrons to leave the electron transport chain because the back door, if you will, the terminal electron acceptor is gone. The back door has been closed. So electrons will start to then accumulate in the electron transport chain. Okay, and so, you know, this process of cytochrome C given up as electrons complex 4 will be inhibited, and then that means the Q cycle will be inhibited, and complex 2 will be inhibited, and complex 1 will be inhibited. Okay, that will lead to oxidative stress, no doubt. Okay, because you're going to start to accumulate lots of electrons in the electron transport chain. Oxygen levels are fine, but they're not being used. So oxidative stress is going to go up in this environment. Okay. Not only that, but something else to mention here is that this molecule, NADH, because it can no longer feed electrons into the electron transport chain, will also start to rise. That will feed back and inhibit the citric acid cycle. Okay. It will also activate pyruvate dehydrogenase complex kinase, which will then inhibit pyruvate dehydrogenase complex. All right. So pyruvate will no longer be converted to acetyl-CoA. Pyruvate will then be converted to lactate, and that's why we see elevated lactate levels. Right? So you see elevated NADH levels, elevated lactate levels, low levels of NAD+. Oxidative stress would be a problem in this. That will probably lead to the tissue damage that was described in the lung and the heart. Okay, oxidative stress, because that's where your highest levels of oxygen are going to be. Not to mention the fact that ATP concentrations are going to be going down as well. Okay, not only in those tissues, but also in your neuronal tissue. Okay, presuming that cyanide can get into those environments. Okay, so very deadly. It's going to kill you, or as one person said, forever sleep. Right. All right. So that would be one way to explain it. Now, you could find a number of other toxins that do actually indeed inhibit this process at some point along the way. Most of them will lead to very similar symptoms. Okay, there are complex 3 inhibitors, there are complex 1 inhibitors that have been noted. Again, NADH levels will rise in those cases. Okay. What's interesting about those is that that electrons will accumulate prior to the point of inhibition in the electron transport chain. Right. So if complex 3 is, for instance, inhibited, then complex 2 and complex 1 will form more of the reduced state. Complex 4 in that case will be more of the oxidized state, because oxygen will be present, and whatever electrons were found in complex 4, okay, will escape, and then there will be no more passage of electrons through complex 3. Okay. So there are lots of different electron transport chain inhibitors, but all of them are going to lead to symptoms similar to that, and they're obviously very dangerous, okay, very toxic. And so the reason I wanted to ask that question is just to kind of help you start to assimilate some of the things that we've talked about, okay, in this class. You could also say the same thing about an anaerobic tissue. You don't even have to inhibit the electron transport chain, but if a tissue goes anaerobic, you lose that terminal electron acceptor, and the same kind of things happen. NADH levels will rise, citric acid cycle will be inhibited, pyruvate will no longer be converted to acetyl-CoA, and lactate levels will rise in those cells as well. Okay. Of course, typically, especially if it's like muscle cells or something like that, it's not going to be deadly. Oxidative stress will be controlled for in that regard, and it's not going to kill the cells. Okay. All right. So, fascinating stuff. Yeah, you got a question?
Is the electron transport chain regulated at all, or is it all just based on the availability of NADH and
Yeah, so the question is the electron transport chain regulated, or is it all just based off of the availability of NADH and succinate? So it's regulated, but not directly. It's regulated by the regulation of this. Okay, so ATP synthase can be regulated, and if the regulation of that goes down, then electron transport chain will go down as well because it's coupled, right? Or if that goes up, then it will, vice versa, the same thing will happen. Okay, and we're not going to talk too much about regulation of ATP synthase, but it can be regulated, yes. Other question, yeah?
How long does it take to die from that?
From the cyanide poisoning? Yeah, so it would depend on the load of cyanide, I would imagine. I don't know, but I would imagine that, obviously the larger amount of cyanide ingested, the quicker the symptoms will set on and kill you. I mean, what you're really talking about is starvation of tissues. And so that doesn't take very long, right, in an active individual. Of course, there would be an ingestion rate and all that kind of stuff. Other questions?